Okay, so it's a pleasure to introduce Boris Hanin from Princeton, and he will talk about neural networks for probabilists.
We can't hear you, Boris.
Okay, I think you can hear me now. Is
Yes.
that true?
Yes.
Excellent, thank you.
Yes.
It's a pleasure to be here. Thanks for the invitation. I want to give a kind of gentle talk. That's my plan. As the people here who know me, like Eviatar, know, sometimes the plans don't go as well as I would hope. But you know, I hope this is kind of informal. So interrupt me if there are questions. My plan is basically to just start with a definition. You know, what is a neural network? Presumably people have heard maybe of neural networks and that they're a thing that people care about. I'm not going to talk too much about the applied side, but I want this to be a kind of a talk for mathematicians where I make some definitions and I try to at least indicate what are some of the connections to interesting areas of probability and mathematical physics and so on. Okay, so at a high level, a neural network is just some family of functions. Okay, it's a finite dimensional family, and I need to set some parameters in order to tell you what this kind of family is. So let me start by doing that definition. Okay, I need to fix some things. So let's fix a positive integer L. That's going to be what's called the depth of the network. And then let's fix L plus 1 positive integers N0 up to NL. These will be what are called the network widths. We need to fix our favorite nonlinear function sigma from R to R as well. Okay, so with this kind of data, I can prescribe to you a finite dimensional family of functions. So definition goes like this. If you want the exact words, it's fully connected. Neural network. Okay, and now I start to get used to use my parameters with L layers. So L usually stands for layers of widths N0 up to NL and nonlinearity sigma. Okay, is any function. I'll often write it script n. It goes from Rn0 to Rnl of the following form. Okay, so N0 up to NL are some dimensions of some spaces, and the inputs to this function are N0 dimensional, and the outputs are NL dimensional. And it's actually a rather kind of simple-minded looking function. Okay, so n of x, I'm going to tell you how to build it up. So I start with my input x, which is an Rn0. And the first thing I do is I apply an affine transformation to it, which I'll call A1. Okay, so I'm going to have a series of affine transformations AL. AL goes from Rn L minus 1 to Rnl is affine. Okay, and more specifically, when I apply it to a vector x, it's just you multiply by a matrix and you add a vector. Okay, that's the notation people usually use. Okay, so now when I apply this affine transformation A1, I'm in Rn1. And to every component of this vector, I apply my fixed nonlinear function sigma. Okay, it's a little bit of an abusive notation, but this is the way people typically write it. So now I still have a vector in Rn1, and now I just play this game L times. Okay, I'm gonna apply the next affine transformation, A2. Now I'm in Rn2, and then I apply the nonlinearity sigma, and I keep going. And then finally I apply my affine transformation AL. Okay, and then depends who you ask and how you set it up. Sometimes at the end you have a sigma and sometimes you don't. And you know, there's no agreed upon definition for this. Okay, so first of all, this might seem like a little bit of a wild definition, but at least I haven't completely lied to you. You know, this is in fact a finite dimensional family of functions, right? Once you fix these things, the depth of the network L, so I should tell you the words people use. So L is usually called the depth of the network, and NL are the widths of the network, or the widths of layers of the network. You know, once you fix the depth L and you fix these widths N1 up to NL and you fix the sigma, this is in fact some finite dimensional family of functions, and it's parameterized by the entries of these weight matrices W and these bias vectors B. Okay, so these are the historical terms people used, and they have some kind of neuroscience background, but I won't tell you about that. So my goal, now that you know what a neural network is, at least to leading order, is to like give you an example, what kind of functions can these things compute, and then tell you how in the world people actually use them. Okay, and then once I do that, I will explain how the idea of the usage of these networks kind of leads to questions in probability and combinatorics and functional analysis and so on. Okay, so let me just start with an example. This is, believe it or not, my favorite example of a neural network. Might be a little strange to have a favorite network, but it's true. Okay, so first of all, the nonlinear function that I'm going to use for this example is what people call the rectified linear unit. Okay, it's a strange historical name, but it's just the function which is the maximum of 0 and t. Okay, so when you use this nonlinearity, what it means is that every time you apply sigma, you have components of your vector, and if the component is positive, you keep it, and if it's negative, you set it to 0, and that's all you do. Okay, fine. So here's going to be my function. So n of x, I'll try to write it in the form that I had. So it's going to be sigma applied to the vector 2, -4, applied to sigma, applied to 1, 1, x, plus 0 minus a half. Okay, plus 0. So here's the matrix W1. It's a 2 by 1 matrix. Here's the vector B1. Here's the matrix W2, and here's the vector, okay, in this case, scalar B2. Okay, so this is some function, and what I'm going to do is I'm going to show you how people draw this function. There's some way so you don't have to write out all these matrices, and then I'll graph this function. I'll tell you why it's kind of an interesting function. But this is just to kind of help build our intuition. So first of all, notice that my input here, the way I wrote it, is just a one-dimensional number, just a scalar. So what you do is you draw a picture from left to right, and okay, if people in Israel had invented this, it would be from right to left, but I draw it from left to right. I can't help myself. Okay, so you think of this input as being the vector x, or in this case, the scalar x. And then you say, look, your first weight matrix is 2 by 1. And so what you're going to do is you're going to draw 2 of these dots, and this is going to represent a 2-dimensional vector, which you get after applying your matrix W. Okay, so you take the entries of W and you put it on the edges of this graph, you get 1, 1. And then you take the entries of this bias vector and you put it on the vertices of this graph, 0 and minus a half. And what you do is you think of each one of these vertices as computing sigma. So this vertex here, the way you read it is you start with x, you multiply by 1, you add 0, and you apply sigma. And that's exactly, this top component, 1 times x plus 0, and then apply sigma. And this bottom one is 1 times x minus a half, apply sigma. Okay, and this is what people might call the computational graph of your network. So it's the computer scientist's way of kind of drawing these functions. So in the last layer, you have 2, -4, and this is the output n of x. And this is, again, has a sigma on it. You want to be very careful, and its bias is 0. Okay, so this is some way that people think about the function that you compute. You start with some input and you process it little by little. And okay, if this is unclear, you should ask me, but I'm hoping it's more or less self-explanatory. It won't be that important for what I'm going to say. But one of the key problems, in a sense, you already see, I think, from this example. Even when I have either of these two representations really for the function that I'm trying to compute, probably unless you're very quick, you have no idea what function I actually wrote down, like in a human computable way. So I want to graph this function to give you a sense of what kinds of things can happen. Okay, oops, let me make this straighter. It's not very straight. There we go. Okay, so first of all, when you write out the function in a slightly more compact notation, you get n of x is sigma of 2 sigma of x minus 4 sigma of x minus a half. And okay, I should have said, I don't think I said this particular sigma, this ReLU, believe it or not, is the most popular one used in practice. Okay, so there's kind of a reason to get a little bit of intuition for it. And what I claim is that when we graph this function, there are 3 interesting. And what do we get? Well, let's see. So when x is less than 0, what happens? Well, sigma of x is equal to 0, and sigma of x minus a half is also equal to 0. So the whole function is identically 0 out here, and we just get a constant function. Okay, so then when x is between 0 and a half, what do we see? We see that sigma of x is x. So this kind of neuron, as they call it, these components are called neurons, is on. But sigma of x minus a half, this bottom one, is still off. So you just get sigma of 2x, which is 2x. So this function has slope 2, and it goes up to the level 1. Okay, very good. And then finally, when x is between a half and 1, what do you get? Well, both of these neurons are on if you want, i.e. both of these sigma just return the identity, and the total slope is 2 minus 4 is negative 2. Okay, so you get a function slope negative 2, and it goes back to down to 0. And then finally, when x is larger than 1, it's identically 0 again because this sigma here it vanishes. Okay, so this is a famous function, at least in signal processing. It's called the triangle function. It's not a very inventive name for it. But one of the things that I want to point out is just that the effect of these ReLUs, or these neurons, is, each neuron in this example causes one of the breakpoints in the graph of this function. And so kind of part of the intuition I'm trying to convey is that each time you apply sigma, your function in some sense becomes more nonlinear. And in this example, there's just a kind of bijection between, how nonlinear roughly the function is and how many times you applied sigma. And so that's the kind of thing that neural networks try to compute as interesting nonlinear functions. Okay, so let me stop. I haven't really told you why this is my favorite example, and I probably won't, but at least I hope it's an illustrative example. So I want to make sure that this is more or less okay what I'm saying before I go on to tell you how neural networks are actually used in practice.
So, Boris, is it always easy to see the order between the breakpoints of the graph and the sigmas on the left-hand side of your board?
No, it is in fact not easy to see. Yeah, I chose this example because it's easy to see. But let me put it this way, when this is maybe like the first connection to some kind of interesting math, roughly, if you study ReLU networks, i.e. neural networks that have this particular nonlinearity, which is piecewise linear like this, many problems become problems in combinatorics. How many of these breakpoints do you have? Other kind of counting notions of complexity. And in fact, it's not completely obvious. If you give me some ReLU network, how many of these breakpoints do I have? What's the most I can have? How many do I have on average? These questions are interesting and largely open in a sense. Yeah. Okay, so yeah, other questions or comments? Like I said, I want this pre-talk to be kind of interactive. I know there's sort of a lot of people, so it's hard to pull.
When the dimension goes up, here we're in one dimension.
Well, yeah, you started in one dimension, you went to 2 dimensions, and then you went back to 1 dimension. So,
no, but I need it's a univariate. What you wrote is a univariate function.
Yeah, that's right. So I needed to be able to graph it.
Of course. No, things become much more complicated when n0 is larger, right?
Oh yeah, so indeed, right. When n0 is larger, these breakpoints become replaced by hyperplanes, or actually slight generalizations of hyperplanes, that cut your input space into a region where a particular sigma is on and off. And the combinatorics of these hyperplanes is quite an interesting question, in fact. Right. That's right. I will hopefully get to that in just a bit. That was one of the things I wanted to highlight eventually. So maybe before I go on, let me say one thing just to emphasize this point. So, people talk about quote unquote deep learning, right? And the reason they use the word deep is, well, it's easier to get a grant, roughly speaking. But okay, what they actually mean by deep learning is just that L is big, the depth is bigger than 1. That's technically basically the definition of deep learning. So it sounds really fancy, but it just means you apply your sigma more than once. And choosing the depth L and these widths NL is what's called choosing the architecture of the network. That's the words that people use. Okay, so I'm going to slowly scroll, and I'm happy to take more questions, but otherwise I want to tell you how these networks are typically used. Okay, so here, what I want to indicate is how to like at least a little bit land the airplane. I wrote down this crazy family of functions, but there's no reason you should think it's actually a sensible thing to study. But this is really what people use in applications, okay, with a few bells and whistles usually attached. And the way these networks are used basically has 4 steps. Okay, so step number 1, at least this is the dominant use case, is what I would call data acquisition. Okay, so data acquisition just means one way or the other, you get a data set, which I'll call script D. And a data set is just a collection of inputs and desired outputs. Okay, K goes from 1 up to capital K. So the whole point here is you don't know a formula for the function f. So f is unknown. But what you know are examples of the value of f at some points. Okay, so like here's an example. Okay, f of x is the indicator function that x has a human in it. So x here, I'm thinking about like a picture you take with a cell phone or something like that. And f tells you whether or not there's a human somewhere in the picture. So this is something that we can do a good job of giving a reliable value for what f is. Our brains do a good job of detecting humans, unless they have camouflage on or something. But if you wanted a computer to approximate this function f, it's a priori not clear how to do it. You know, to a computer, an image is just a bunch of pixel values, and it's not clear what you do with like any particular pixel. You know, what functions do you even apply to the pixel to get some sensible answer? Okay, so your goal was to find a good approximation for this function f. So the second step is you choose a hypothesis class. Okay, in this world, they call it architecture selection. So you basically say, well, I don't know the function f, but I hope it can be approximated by a complicated neural network. So basically, at least in this very simple-minded set of examples I'm giving, this means you fix the L and the widths and the sigma. And all this means is that you get some finite dimensional family of functions. You know, it's some nonlinear space of functions that can be computable by your network that has this fixed architecture. And what you're hoping for is that there's some place, let's say this place, which happens to be a good approximation to your function f. Okay, how to do this is not so easy, and you can kind of start to imagine that questions about what functions are in these function spaces are interesting questions in things like functional analysis. Okay, but so far you still haven't done a good job of finding good approximation to f. And so this is roughly speaking where the probability theory comes in, or where part of it comes in. So step 3 is initialization. So what does initialization do? Well, it says, I have no idea what a good approximation to my function f is. So I'm going to start at a random point. Okay, so you choose, I'll call this vector theta. Okay, so you choose all the weights and biases in your network at random. Okay, and exactly how you choose it at random is actually quite an interesting question, and so on. But for the purposes of what I'm saying here, I'm just saying there's some probability measure on this interesting high dimensional space of functions, and this is the measure you start with. Okay, so at the start of training, you know, you select some theta 0 if you want. That's the beginning of your optimization process. And of course, the particular value theta 0 you selected, you know, corresponds to some function computed by your neural network, but it's not as if actually this function has anything to do with anything you care about. You haven't used your data yet. So now you have to use the data, and that's the 4th step. Okay, so this is what you might call optimization. And the purpose of optimization is to update your parameters. So you update the values of this vector theta, which encodes, you know, which function you're currently computing. And the kind of crazy thing, in a sense, is that in practice, this is always done by gradient descent. So you do it by gradient descent, right? Which literally means that, you know, theta at time t plus 1 is theta at time t minus a step size eta times the gradient of some function with respect to theta, you know, evaluated at theta equals theta of t, where you have to also tell me this loss function, as they call it. And always in practice, you choose an empirical loss. So you do gradient descent on an empirical loss. Okay, empirical just means it's an average loss over your data set. So maybe L on your data set is the average over the data set of some loss. I'm just going to choose a random one. Okay, so the function you currently compute, so this is at the current value of trainable parameters theta. So this is xk minus what you're supposed to compute, okay, maybe squared. Don't take this too seriously. I'm just saying what you do is on every data point you have, oops, this should be a k here. So on every data point you have some way that you decide to measure the error. And the function you try to minimize is the average error over your data set. That's the kind of thing that you literally optimize by gradient descent. Okay, so somehow if I were to continue this slightly ridiculous picture that I have, you know, what you do is you start moving theta, and who knows, maybe it tries to go around, and then you hope it gets to like some good place where the value of theta actually implements a function that approximates f well. Okay, so that's really how neural networks are used. Okay, of course I've lied about a lot of little things. It's more complicated in practice, but these are the basic steps. And somehow the point is that, you know, at least a lot of the probability enters at step 3. And, you know, what you see is that at the beginning of your training process, your weights and biases of the network are random. And, you know, you basically have some interesting probabilistic model that has large random matrices in it. And what one can imagine doing some kind of analysis from that point of view, which I will explain a bit now. Okay, so let me again stop for a second and ask if there are questions. And then I will try to start connecting this to like concrete questions and areas rather than just talking about vague applied stuff.
Probability enters just in the third step. That's once you do it once.
Sorry, can you speak up a little bit? I couldn't hear you extremely well.
I said probability enters in the third place only. You just choose once the probability measure and then you forget about it. Is that correct?
Well, okay, that's not completely right. So typically you assume the data generating process itself is IID draws from some distribution. So your function f might be a random function, and the values at which you get access to f are often also taken to be random. So, and as I'll say in a moment, that's important because typically the data set size is large. So there's kind of a lot of randomness there. But it also turns out that the way people do optimization in practice is stochastic. There are various random choices that they make, and that's quite a world of kind of interesting questions, in fact, that I won't get into very much. But still, if I had to identify the most important probabilistic thing, it's going to be in the initialization. I think that's probably fair, but yeah, this is a more complete sort of answer to the question.
Another question, what are the architecture that is used in practice? How long does it take to actually run this process? Can you do it for big values of L and NL and so on?
Yeah, so that's a great question. So let me write here, that was what I was going to do anyway. So salient features, like how should you think about what's big and what's small and what's important? Yeah, so the first salient feature is the following. Everything is large. Okay, so the data set size, maybe I'll write it this way actually. So the number of data points is typically very large. The number of parameters you have in your network is typically very large. And when I say large, I mean very large. So I mean, there are these kind of amazing natural language models that people have been coming up with recently. And, you know, they might have 5 billion parameters in them. So you're doing optimization over a 5 billion dimensional space, you know, so that's sort of wild. Okay, so the data is large, number of parameters is large. The input dimension is typically large or can be large, you know, a high resolution image, you know, if it's n pixels, then it's like n squared times 3 is the input dimension, right? You have n by n pixels and you have 3 color channels. And so if n is like 100, that's actually very high dimensional. So that's large. Typically the depth is large. That's when they say deep neural networks, they mean L is big. And in fact, the widths are large as well. Okay, and so as you can tell, there are many, well, and training time is typically very large, depending on how you measure time, of course. There's parallelization and all that. So, but I mean, number of steps of training can be fairly large too. So there's a lot of large parameters, which should be good for mathematicians, right? It's hard to study things not perturbatively, but when things are large, maybe you can say something. But yeah, everything is large, and that's sort of, you might say this is like, big data or whatever. People use all kinds of buzzwords. Okay, so that's salient feature number one. Salient feature number two that I want to point out is that this function L that you're minimizing is not convex. So part of the questions that come up about neural networks is, why is it that you can, by a first order method like gradient descent, with high probability find, an approximate global minimum, which is what you find in practice for a non-convex function? I mean, these things are not impossible, right? That's what happens for spin glasses, for example. But you have to like say something non-trivial about why that should be possible. And then maybe the third thing to say is that although both the number of data points is typically very large and the number of parameters is very large, in fact, the number of parameters is typically much larger than the number of data points. And, that should sound a little bit weird potentially. I'm trying to solve a system of 20 equations using 1,000 variables. So okay, makes sense that maybe I can do that, but why I find a reasonable solution is not completely clear. So I didn't mean for this to be a statistics talk or an optimization talk for that matter. So I won't go too much into 2 and 3, but these are like the somewhat surprising features of how these things are used. So I hope that sort of answers the question. Yeah, other questions? This is moderately clear. Okay, so, I hear a question.
So does the random initialization help avoid local minima? Because I could have started, say, if you want to find a human, just take 100 photographs and give the function value 1 on each photograph that has a human and 0 otherwise, and start initialization of that. So why is the random initialization better than some supervised initialization?
Well, it is not completely clear why random is better than smart. In some sense, well, the reason random is better is that it works in practice. That's about as good of an answer as I can give you. And there are some theorems which say that in certain setups, with high probability, you can in fact drive the loss to 0 and so on. So there's some understanding of this, but it's certainly not complete. Yeah. So okay. So I'm happy to take more questions, but I'm going to slowly start telling you some math because I feel very self-conscious that I haven't actually said anything precise yet. I've just been waving my hands at things. So let me, so maybe I'll call this section intuitions. So this is like an attempt to connect various aspects of neural networks to cool things in math. And that's sort of, in a way, how I got into it. I realized that many questions I was interested in come from things I secretly already knew about. Okay, so intuition number one is I want to explain a connection to random matrix theory, and specifically to products of random matrices. Random matrix products. Yeah, so actually this connection is much deeper than what I'm about to say. So just take this as a shadow of something I could talk about more extensively, but didn't want to take the time to do it. I'm happy to do that offline if you're particularly interested. Okay, but let me just say it this way. Let's consider a special case, a very special case of these neural networks. So let's take the biases to be identically 0, and let's take the nonlinearity to be in fact linear. Okay, that's a function from R to R. It's a particularly simple function, of course. So in this case, the output of your neural network just looks like this. It's a product of random matrices applied to your input vector X. And okay, so at least at the start of training, so at the start of training, WLIJ are IID. Okay, they're IID Gaussians, let's say, or IID whatever you like, with mean 0 and the correct variance. But I don't even want to get into the details. I'm just pointing out that there's a special case of these neural networks, which at least at the beginning of training, which turns out to be kind of very important for understanding neural networks even after training, are just IID matrices. Okay, so these kind of matrix products have been studied forever, really, like, since the 60s for sure. But they're mainly studied in kind of two different regimes. So let me sort of illustrate this with a picture. Okay, so the analogy I like to think of is one from dynamical systems, where you say, okay, you have a very, very chaotic dynamical system. And in this dynamical system, the time one transition map is obtained by multiplication by a single random matrix. Okay, so from this point of view, L is like the time parameter. So I'll draw that on the x-axis. And okay, I will simplify the picture further. I should have said all of my NLs are the same, just for simplicity. Doesn't actually matter too much, but it makes the analogy cleaner. So and then N is the system size. It's literally the number of degrees of freedom in your dynamical system. And what you're doing is you're studying kind of the behavior of random dynamical systems, or very chaotic dynamical systems, where you have two parameters, which is the size of the system and the time you view the system evolve. And okay, mathematically, this kind of thing has been studied forever. So kind of up here, this is the free probability regime, right? You fix the number of terms in your matrix product. Maybe capital L equals 1. That's very classical, but maybe capital L equals 12 for some unknown reason. And you send n to infinity. And you're studying, for example, the spectrum of random matrix products. So that's nice. That's a classical regime. And then there's the opposite regime, where you fix the system size and you study the long time behavior of these dynamical systems. So that's also sort of an illustrious thing. And this is like an ergodic regime. So maybe I'll say this is like the multiplicative ergodic theory. And my point, all I'm saying is that neural networks are somewhere in between. Okay, so in neural networks, capital L can be very large. The widths of these layers, i.e. the size of these matrices, are also potentially very large. And moreover, what you're really interested in is finite width effects. So kind of the challenges, roughly speaking, for studying matrix products in this regime is that, first of all, you have to balance the trade-off between L and N. And the second is that L and N are both finite. So, in the ergodic side, what you're asking for is finite time corrections to the ergodic theorem. And on the free probability side, you're asking for finite size corrections to free probability. And both are interesting and non-trivial subjects and so on. Okay, so I'm not really explaining the full breadth of how random matrix theory comes into studying neural networks, but I'm just pointing out that at the start of training, the matrices you have, these W's, are literally initialized in practice to have IID mean 0 appropriate variance entries. And so various things about your network ultimately come down to studying, either exactly questions about products of random matrices or things related to products of random matrices. Okay, so that's sort of the first connection. That's actually the way I really got into neural networks, is I took a particular problem called the exploding and vanishing gradient problem, which is something about the numerical stability of gradient descent. And I proved that, at least for ReLU networks, it's exactly about products of random matrices, like IID random matrices. And then for those random matrix products, I was able to prove some kind of new theorem and get some interesting information about neural networks as well. Okay. So yeah, let me actually indicate one extra thing. So I'll say challenge number 3. I will sketch something about that. So for general sigma, you can do the following. So you can compute the derivative of the network output with respect to the input. Right? No one can stop you. You can do it. So this kind of thing is a product of matrices. So there are some extra matrices that appear in general, which are the identity otherwise. Okay, so these DL matrices are just diagonal matrices whose diagonal entries are, sigma prime, evaluated at, the values of the network after L layers. Right. So all I'm saying is that a neural network is a composition. So when you take the derivative, you get the product of the Jacobians. And the Jacobian of your affine transformation is just the weight matrix. But the Jacobian of applying your fixed nonlinearity sigma to every entry of a vector is just sigma prime. You know, it's a diagonal matrix with sigma primes in it. And so this is kind of a third challenge that in general, when sigma prime is not equal to 1, like it is for linear networks, these matrices DL are sort of complicated. So the challenge is that these matrices DL are not independent, of course, of W1 up to WL. You know, they depend on the previous affine transformations that you had. And so you have to deal with that. And it turns out to be dealable with. But that's sort of in the slightly more general connection between random matrix products and neural networks, a key point. Okay, so that's the end of this first intuition. So let me again ask if what I'm saying is clear and if there are questions about this. And then I'll give you a couple more intuitions, things about optimal transport, things about combinatorics of hyperplane arrangements, and so on. So let me maybe actually go back to this slide here, say one thing which I realize I should have said, but I didn't. So let me add one salient feature, which will maybe help to motivate why it's interesting to study the kind of neural networks when everything is completely random. These weights and biases are random, like at the start of training. So it's already secretly in these salient features, but let me make it explicit. So because the number of parameters is very large, what this implies is that you have concentration of measure. Okay, this is of course a very rough implication, but this is intuitively what you should imagine. So this probability measure, you know, this yellow thing that I drew at the start of training, is like a measure on 100 million dimensional space, roughly speaking. And so of course it's very concentrated. Now it's not completely clear what it's concentrated around, but nonetheless. Okay, so somehow, first of all, it's interesting to study this measure, and that's really what I'm talking about when I talk about these random matrix products most directly. But the second thing is that because the number of parameters is larger than the number of data points in practice, what you can kind of heuristically conclude from this is that the parameters don't need to move too much during training. And that's basically true in practice as well. And it's what allows you to use information about the start of training to say something about the end of training as well. You know, if you have 1 million parameters and you're trying to fit 3 equations, you don't have to move each parameter too much to actually fit the equations. Somehow there's a ton of room there. So again, this is just meant to be additional motivation for why one would be excited about studying the case where you're starting training, you know, at theta 0. The way I drew this long optimization trajectory, but that's just because I prefer to be theatrical, roughly speaking. Okay, it doesn't necessarily have to be long, or it could be, you know, but in many cases it isn't. So that's sort of a point I should have made, but I realized I didn't make. Okay, so back to this. Okay, so that's all I want to say about random matrix products. Again, if you're interested in actually learning the details about this, tell me, and I'll send you papers, or we can just talk separately. And there's a lot of beautiful questions here. Okay, so that's connection number 1. Connection number 2 is I want to explain how one-layer networks are related to optimal transport. So unfortunately, this, as far as I know, is only true in the case when capital L equals 1. But still, there's kind of a beautiful idea here. And I want to say something about it. Okay, so when you have a neural network with only a single layer, you know, the function it computes looks like this. So I'm going to drop the kind of large, or the bias term in the output, and it just looks like the sum on j goes from 1 up to n1 of aj sigma of wj dot x plus bj. And I apologize for changing the notation, but it's just less cumbersome this way. right? So all I'm saying is you start with an input vector x, you take its dot product with a bunch of rows of your first matrix wj, you add offset bj, you apply your nonlinearity sigma, and you take some linear combination of this. I've written something that has output dimension 1, just a scalar valued function. So this is basically the general form of a neural network with one layer. So just to be clear, x and wj are both n0 dimensional vectors, and then aj and bj are scalars. Okay, so what I want to point out now is that there's kind of a very simple but quite powerful, actually, dictionary between neural networks with one layer and certain kinds of measures. And this dictionary is what opens up the door to lots of interesting things, in particular to studying sort of neural networks via optimal transport. So you can also write this neural network output as an integral, right? You can write it as the integral of sigma of w dot x plus b against a certain measure, d mu n of wb. And of course, mu n of w and b is just a sum of delta functions. J goes from 1 up to n1, aj delta function of wj bj. Right, that's true. That's what we teach our calculus students or whoever we teach. That a sum is an integral if you're just sophisticated enough, basically. But rather than making fun of it, let me just say that this is a way of making a dictionary between neural networks with one layer and certain kinds of measures. In fact, very simple measures, just atomic measures, finite linear combinations of delta functions. Okay, and here's the point. The point is that given a target function, so suppose I'm trying to learn some function f, so I'll write it as f of x. I'm going to write it in the same form, sigma of w dot x, plus b against some measure determined by f of w and b. Okay, so there's some general theorem which says that for any reasonable function sigma, practically every single function admits a representation of this form. In other words, given a sensible function f, you can find a sensible measure mu f so that when you integrate against this sigma of w dot x plus b, you return f. And that's not crazy, like just think of the Fourier transform or something like that. You can easily recover f as long as it's a sensible function by functions that look like something applied to various vectors dot x. So this is some generalization of like Fourier inversion, roughly speaking, and it's some classical easy fact. Okay, but here's what I want to say. If I give you a target function and I write it in this same kind of form, that's the function I want to approximate, and this is the kind of function I get with my neural network. So I'm allowed to kind of choose this measure with n1 atoms. Then the following happens to be true. Okay, so as n1 goes to infinity, so this is like the free probability limit if you want, or the mean field limit or whatever. When you do gradient descent, so when you're actually training the network, gradient descent on the L2 loss. So this is just the loss I had where the error is measured just by the average of the squares of the errors that you make on your data points. What you get is that the dynamics, like the full training, become optimal transport. I'll say to this measure mu f. Let me just put it that way. Okay, so it's like you start with some random starting point. You have some random sum of delta functions. That's the initial measure you're starting with. And of course, in the limit, as you take the number of delta functions to infinity, you actually get some nice, reasonable starting measure that has a smooth density. And what it turns out is that actually the full training procedure for neural networks, when you actually do gradient descent, comes down to optimal transport between that starting measure and the target measure you have, this mu sub f. Okay, so this is again just like a small shadow of a large dictionary where you can take any question you want to answer about neural networks, at least for one layer networks, and using this kind of very simple formula, you can translate it into a question about some space of measures. You can imagine all of these delta functions as living in like some space of finite signed Borel measures or something like that. And in this one kind of infinite dimensional space, you start having analysis problems now, saying, what's the dynamics in this case of optimal transport, which is hard but has been well studied. Or you might get questions like, what kinds of measures can be represented in various ways? And that's like questions in functional analysis, roughly speaking, and so on. Okay, so this is quite a useful dictionary to know about. And I think it connects to lots of nice stuff, but the main limitation is that at least I've never seen a usable form of this dictionary between, the network function and this measure mu sub n that works beyond one layer networks. I know there's been some recent work on it, but as far as I could tell, it just wasn't as user-friendly as this. Okay, so again, let me stop for a second, ask if there are questions about this. I'm just trying to, give some sketch of things rather than go into them too deeply, but I am happy to say more if people are interested.
And you still have here non-convexity problem?
Yeah, that's right. Optimal transport is not a convex thing. And certainly, so I'm sliding under the rug like an important point, which is that, what I've said here is I've snuck this in, as n1 goes to infinity. And it's not completely clear a priori what I mean by that in some very precise way. And there's always this slightly, technical step of you have some limiting procedure, which is some nice continuous thing maybe you know about, maybe optimal transport does something good. But now I'm basically saying, take your optimal transport trajectory and take some measure and now discretize it, replace it by a sum of n delta functions that approximate that measure. And now say that there's some discrete dynamics which approximates the continuous dynamics. And certainly after you discretize, all hell breaks loose and nothing is convex anymore and so on. And you have to deal with it. Yeah. But yeah, okay. Let me not say more about that, but I think that answers your question. So there's still some essential non-convexity, but somehow smart people have thought about optimal transport for a while. And the things that were non-convex are at least largely understood or understood well enough to say something non-trivial here. Okay, so let me give one last example, which is very fun, at least for me. So let me do this thing which I said about connecting neural networks to hyperplanes. So the third thing is hyperplane arrangements, and actually generalization of hyperplane arrangement. So, okay, so hyperplane arrangements basically are the thing that happens for ReLU networks. So let's consider the simplest case first, a one-layer ReLU network. And this is one of the questions that was brought up in the very, very beginning. Okay, so let me remind you, first of all, that ReLU just means that sigma of t is the maximum of 0 and t. And again, the network function looks exactly like it looked before. G goes from 1 up to n1, aj sigma of wj dot x plus bj. Okay, and here I want to think of x being in Rn0, and I want n0 to be greater than 1. I can only really draw the case n0 equals 2. But already the complexity is there for n0 equals 2. So what I want to say is the following. Okay, to each one of these neurons, as they're called, to each j, I can associate in a natural way a hyperplane, which is the set of points x where this thing turns from being negative to positive. Okay, so let me define hj is the set of x such that wj dot x plus bj equals 0. Okay, so that's a nice hyperplane, and I can draw these hyperplanes, or I can draw some hyperplanes and call them these hyperplanes. So let's say this is h1, this is h2, and this is h3. So the first thing is that given a ReLU network, you get some hyperplanes, and these hyperplanes tell you when different components turn on and off. If you're a little bit more careful, what you see is that it's actually a co-oriented hyperplane arrangement. So these things come with some arrows, which tells you in which direction, the thing is turning from on to off. And roughly speaking, these hyperplanes partition the plane into these convex cells. And on each convex cell, each component of this sum is either the identity or it's 0. So the whole function you compute is just an affine function when restricted to each particular cell of this hyperplane arrangement. Okay, and you can think of this as some kind of Hamming code looking thing. This is like the 111 cell. All three of the neurons are on, right? And then when I cross the H3 hyperplane, this is like 110. And then when I cross the H1 hyperplane, this is like 101. And then I get 000. And then I get 100. Hopefully I don't make too many mistakes. 001 and 011. I think I made it right. Okay, so I'm saying you get some decomposition of your input space, which has some nice combinatorial flavor. And on each one of these pieces, the function you compute is some linear thing. And then the linear function changes on the different pieces. Okay, so this is like version 1.0 of the dictionary between ReLU networks and kind of interesting combinatorial questions about decompositions of spaces, when you partition them up into convex cells. But the thing I want to point out that, I'm sort of running out of time, so I won't go into it too deeply. But still, so if you added one more layer, so let me give myself a different color. Maybe I'll use blue. So this was for one layer networks, but imagine I had several layers in the network. So I can still associate to every kind of component in the first layer one of these hyperplanes. No one can stop me. But now there are more hyperplanes that I have to associate to components that are in future layers. And the basic point is like this, right? On each one of these cells, for example, on this cell here, the function that goes from the input through the first layer all the way to the second layer is linear. And the reason is that, on this cell, every kind of component in the first layer is replaced by either the identity or 0, just by something affine. And so what that means is that in here, components in the second layer look like they came from the first layer. So I get some hyperplane, where a particular component turns from on to off. But the point is that now this hyperplane interacts with hyperplanes from previous layers, and it bends when it meets them, because you get a different affine function every time you're in a different cell determined by the first layer. So I'm not saying this very concretely, and I sort of apologize, but what I'm saying is there's a dictionary between general ReLU networks and these kind of funny looking bent hyperplane arrangements. Okay, so they still partition your input space into these convex cells. Every cell you get is convex. And on each one of these cells, the function you compute is just some affine function. But now there's some interesting kind of global relationships between these cells because they came from hyperplanes and so on. Okay, so this is kind of largely unexplored, but it opens up quite a number of questions of the form. If you give yourself a random ReLU network, you get some random partition of the input space into these kind of beautiful convex cells. And you might ask, like, how many cells do you have? What are the sizes of the cells? Okay, and so on and so forth. And these questions, like, only like epsilon squared of these questions have even been thought of, let alone answered. And I think there's quite a lot of fun stuff there. So again, if you're interested in that, I can talk to you about it separately, and I can tell you what's known and what I think is interesting, which may not be reflective of what's really interesting, but it's all I can really do. Okay, so let me stop. I think I should stop and take questions and take a 3-minute break before the main talk.
Are there any empirical results on how many cells you have as a function of the depth and width of the network?
Yes, there are empirical results, and there are also theoretical results. So, okay, I should say this: hyperplane arrangements have been studied forever, in combinatorics at least, and the number of cells in a hyperplane arrangement is a well-known function. It's a theorem of Zaslavsky from like the 70s or something like that. But of course, in these deeper networks where the hyperplanes start bending and things are no longer so algebraic, it was not known. But what it turns out is that on average, the hyperplanes don't bend too much, and you get as many cells as you would have gotten if they were all hyperplanes that were completely straight. But then there's a question of the variance, and the variance indeed increases, and it's unclear how exactly it increases. No one's been able to prove that, and it's not so easy to actually do numerically because the number of these cells can be extremely large. Like especially if you insist on counting this on the full input dimension. If your input dimension is like 700, the number of cells grows like exponentially in the input dimension. And so if you're trying to count 3 to the 700, versus 4 to the 700, you've made a huge mistake somewhere in your life. Yeah.
Okay. Any other question before we take a break for the second talk? Okay, so let's take a 5 minutes break and return to the second talk. 15 minutes. Hey, Boris, are you ready for another round?
Sure.
Okay, so we're very happy that Boris agreed to both to wake up very early and to give us 2 talks. His next talk is titled Neural Networks, You're Hiding Large Width and Finite Depth. Thank you, Boris.
Right. Yeah, thanks. Okay, so I tried to make the last talk gentle, in part to compensate for the fact that I anticipate this talk won't be that gentle in a sense. But let me just say a word actually about this project. It's a bit of an unusual project for me. So I've been working on this for a while now with 2 really amazing physicists named Dan Roberts and Sho Yeda. So both Dan and Sho are high energy physicists by training who started working on machine learning questions as well. And so what I'm going to present is kind of the results that we've gotten so far. Everything we did in a kind of physicsy way. So I'm going to state some things which I'll call a P theorem, so a physics theorem. Okay, some of them I already know how to prove as actual theorems, but many of them I don't. And my goal is kind of just to try to state what I think is a really interesting model that comes from neural networks for a set of stochastic processes to study. And I'll tell you what we know about them, and hopefully you'll get excited and study them as well. Okay, so let me start with the model. And if you were at the last talk, this model will seem very familiar, but I won't say anything about why I care about this model non-mathematically. So to specify the model, I need to fix some parameters like I did before. So I need to fix a positive integer capital L. I need to fix L+1 integers n, 0 up to n capital L. I need to fix a function sigma from R to R. I need to fix 2 positive real numbers, CB and CW. Okay, so here's going to be the model. I'm going to define for you kind of a Markov chain of stochastic processes. And my goal is going to be to study this Markov chain. And these stochastic processes are what a neural network with random weights and biases computes. Okay, so for an input, for a starting value of this stochastic process, so I start in Rn0. I'm going to recursively define the following thing. So I'm going to write Z0 alpha. It's another name for X alpha. That's the starting point. And then for general L, I'm going to write ZL alpha to be a matrix WL applied to my nonlinear function applied to the previous vector. So ZL minus 1 alpha plus BL. So first of all, so these matrices WL are NL by NL minus 1 matrices. BL is an NL dimensional vector. And just like in the previous talk, when I say apply your fixed nonlinear function sigma to a vector, I just mean apply it to every component. Okay, so these matrices have random entries. So Wij are all Gaussian with mean 0 and variance CW over NL minus 1. And BLJ are Gaussian with mean 0 and variance CB. Okay, so these parameters CB and CW are the variances of the entries of these matrices W and the components of these vectors B. And in this way, I have some vector valued, Markov chain of stochastic processes. Okay, so just to be very clear, let me just add one more piece of notation because I'll use it, but also hopefully it will clarify a little bit what the parameters are. So when I write Z with a superscript L and I write I and then colon or semicolon alpha, okay, this just means the ith component of, ZL alpha, which comes from the input X alpha. Okay, so this alpha corresponds to, that's how I just call my inputs. I give them Greek letters, and then I try to reserve the Roman letters like I and J for the components of these vectors. And then the superscript L is telling me sort of how far along in the time parameter, roughly speaking, I am in my Markov chain. Okay, so that's the notation that I'll use. And my goal is basically to analyze this stochastic process, you know, ZL alpha, when, well, you know, the N1 up to NL minus 1 are all on the order of some large parameter N, with N is large, and L, you know, is small or large. I'll be interested in both cases. Okay, so just to be clear, the way I'm setting this up is I fix this input dimension N0. It's like the starting point. And I fix, if you want, the output dimension, the final time N sub L. But I take all the ones in between to be large. And you can just think of them as a fixed large number N. I read it this way just for completeness, basically. And I'd like to understand what the behavior of this stochastic process actually is. And
what is your alpha?
So yeah, alpha is the starting point of the Markov chain. So so if you want to think of it as a stochastic process, I call the inputs to this stochastic process X alpha. It's like a function of, I just don't want to write a notation like, I could write ZLI of X alpha. That's what I mean, but it's just annoying to have even more notation and to write X alpha everywhere. So when I have this alpha down here, it just means there's some input that I called X alpha. That's the starting point.
Alpha is running from where to where?
So I mean, you know, well, there are uncountably many things in Rn0. So alpha is something that indexes Rn0, if you want. You know, like I'm just saying X alpha is in Rn0, and X alpha is arbitrary, but I give it a name so that I don't have to keep around the whole X dependence. So like, let me give you an example. Okay, when I write the covariance of ZLI alpha with ZLI beta, what this really means is it's the covariance of ZLI at X alpha with ZLI at X beta. That's the kind of notation that I'm trying to use. Is that okay? Does that answer the question?
Yeah, that's fine. Yep.
Great. So yeah, that's the notation I'm super used to now, and it's kind of the physicist way. You dump everything into components, roughly speaking. So this is my goal. I want to analyze this stochastic process, and okay, I came to this because I'm interested in neural networks for various reasons. But like I said in the last talk, let me just point out a very special case of this. Okay, so if your function sigma is just the identity, and you set the bias variance to be 0, then the output of this Markov chain is just a product of random matrices, WL down to W1 applied to the input X alpha. Okay, so this recovers as a very special case, studying products of random matrices. And you know, products of random matrices are a subject that has been widely studied, but actually, you know, there are quite a number of interesting questions that arise even in this kind of linear context that haven't really been understood before. But adding the sigma into the game really makes it harder. But it turns out to be still studyable. Okay, so here's sort of the main point. Okay, let me skip to the end and tell you what I want to say, and then I'll try to say it in some detail. So the TLDR is that you study ZL alpha, okay, perturbatively in this parameter N inverse and recursively in L. So as I'll explain in just a second, when you send these parameters N to infinity, ZL actually just becomes a Gaussian process. And so that's the starting point. Everything is very easy in the infinite width limit in a sense. But then what we do is we actually study all the corrections to this Gaussian process. And this thing becomes exactly solvable. Okay, so you can study this and we find the solution, or, in a physicsy way, we find the solution at all orders in N inverse. Okay, there's still quite a number of questions we don't actually know how to do, but at least if you just want the distribution of the kind of output of this Markov chain, we can give you really the full corrections to it, or at least some mechanism to compute them all. Okay, so that's what I'm trying to get to, but let me set it up little by little. So let me tell you what are the two most important, pieces of structure for this stochastic process. So the first thing I already said, right, ZL alpha is a Markov chain with respect to L. And that's pretty obvious, right? If you were to give me ZL minus 1, of course, that fully determines the distribution, or the values, if you want, of ZL. I don't need to know the previous ones, and that just follows directly from this one-step recursive formula. So that's easy, but that's useful. It means that ultimately we're going to study things by transition probabilities. Okay, but the second thing is that this is not some arbitrary vector valued thing, which would be insane to study. The point is this has a ton of independence already built into it. And the reason it has so much independence is that these matrices W and these vectors B are all independent of each other. And the kind of most direct way of saying it is like this. Okay, if you look at the finite dimensional distributions of this process, so for any set, which I'll call X sub A, so these are X alpha, alpha in A, of initial states or inputs to the stochastic process, what do we find? Well, we find that this collection ZLIA, okay, so this is I goes from 1 up to NL. These are the components of my stochastic process at time little l, by which I just mean like ZLI alpha. Alpha is in A, okay, I goes from 1 up to NL. So each of these guys, the values that a particular component of this stochastic process computes are independent of each other, conditional on the previous thing, right? So our IID, if you give me ZL minus 1. Right, and again, this just follows directly from this formula, right? If you just consider ZL minus 1 as some given thing, then, because the entries of the W matrices are IID, of course, the components are going to be IID as well. And so somehow there's a ton of conditional independence built into these transition probabilities. The transition probabilities from time L to time L plus 1 are conditionally independent for the different components of your stochastic process. And that's hugely helpful. And that's ultimately, the structure that we use to unravel what happens. Okay, so let me stop for just a second. Again, like to make sure that at least the setup of the problem is clear. It might not be clear why I care, but hopefully, you were at the last talk, or you just trust me, or some, convex combination of the two. Okay, so I can't tell if everything is so clear that there are no questions, or it's so unclear that it's not clear what to ask. But okay, I encourage people to interrupt me because, why not? All right, so let's go to the first kind of set of results. So this is what I'll call the analysis at finite L. Okay, so the point of view here is that I fixed some value of capital L. I'm not interested in the long-term behavior of my Markov chain. And I would just like to understand what is the distribution at a finite time. Okay, so I'm just going to remind you of the recursion. ZL alpha is WL sigma of ZL minus 1 alpha plus BL, just so that the notation can be kept around. Okay, and there's a theorem here. And this is a real theorem, and it's not our theorem. In fact, it was proved in various ways by quite a number of people. There's someone called Radford Neal who proved some very easy version of it. Then there's some physicists who worked on it. Then there are some computer scientists who worked on it, and okay, so on. But the point of the theorem is very simple. Okay, so as n1 up to nl minus 1 go to infinity, this stochastic process ZL alpha converges to a Gaussian process, in fact, to a centered Gaussian process. So remember, this is some vector. It's an NL dimensional vector. So you get some Gaussian process, but actually it's very easy because the components of this Gaussian process are actually independent. Okay, so with IID components and the following covariance. Okay, so for the 2-point function, I'll write it this way: KL alpha beta is equal to the covariance of ZLI alpha with ZLI beta. Okay, so this is literally the 2-point function of your process. And notice here that I've forced the components to be the same because I told you it's 0 if they're different. The components are independent. Okay, and the point is that this thing satisfies a recursion, okay, which satisfies a recursion. Okay, so you get K L plus 1 alpha beta. So the covariance at time L plus 1 is equal to CB plus CW. These are 2 parameters in the model. And then, okay, I'm going to introduce a piece of notation that I will explain immediately. Then it's a Gaussian integral with respect to the Gaussian process at the previous layer. Okay, so whenever I write these angle brackets, this just means Gaussian integral. Okay, so specifically I take Z alpha and Z beta, 2-dimensional Gaussian, drawn from a Gaussian with mean 0 and the covariance kernel at the previous layer. And I do this thing. So the way you're supposed to read this recursion is, if you knew the 2-point function at time L, and I told you the values of CB and CW and your nonlinearity sigma, you can read off the values of the covariance kernel at time L plus 1. And this recursion is not that simple. It's not a linear recursion, right? The dependence on KL here is nonlinear due to the fact that sigma is not linear in this integral. But it's a nice recursion, and we'll come back to it. Okay, so this is a classical thing, and this is really not very surprising, right? Here, each component of ZL alpha is just some large linear combination of things from the previous time, right? This W matrix is getting bigger and bigger and bigger. That's the fact that the n's are going to infinity. And so it's not too surprising that some large linear combination of weakly correlated things will give you a central limit theorem and you'll get some kind of Gaussian process. This is not that surprising. Okay, and the whole point for us was to try to understand what happens when you do perturbation theory around this Gaussian process, when you actually try to ask what happens at finite but large values of these widths n1 up to nl minus 1. Okay, so there are a number of reasons to do this, but when you use neural networks in practice, which is where this thing comes from, the neural networks are not infinitely wide. And this kind of Gaussian limit turns out to be too rigid, too simple-minded to capture important things about how neural networks actually work in practice. So okay, I won't say too much about that, but if you're interested, again, I can give a kind of coherent discussion of that afterwards, or just at some other time. Okay, so the question is, you have this sequence of Gaussian processes indexed by L, and you would like to systematically do perturbation theory around a Gaussian process. And the question is how you do that. And okay, there are many ways to do perturbation theory around a Gaussian process. But okay, I'll say here's the idea, and I'll attribute it to my collaborator Shou. He's the first to kind of really implement it in this context, but it's presumably one of the first ideas that a probabilist would have, is you say, okay, a Gaussian process is characterized by the fact that all the higher cumulants of its finite dimensional distributions vanish. So we're just going to organize the corrections by studying the higher order cumulants. That's a natural thing to do. Okay, so in mathematician speak, what Shou did is he says, organize the corrections to the Gaussian process by studying the higher cumulants. Okay, so studying the higher cumulants of a stochastic process is like fine. It just requires a little bit of notation, just because there's lots of indices floating around. So let me write down the definition of what I mean by higher cumulant, and then I'll give you some examples, and you'll know it better than I do after I'm done with the examples, basically. Okay, so let me fix a collection of indices I1 up to Ik. So these are like, this script I is a collection of components. So, right, so Z is some vector valued thing, and I have to tell you which components I'm comparing. And this will be the components that I compare. So IJ, go from 1 up to NL. These are the components of the thing at time little l. And then I have to fix some collection of inputs, alpha 1 up to alpha k. So X, alpha j are kind of starting states, or points at which to evaluate my finite dimensional distributions. Okay, and then the definition of the higher cumulants, and I'll just write them like this. So I'm at time little l, and then it's the kth cumulants, which is why I put a little k there, and then it corresponds to these two collections of indices. So it's defined in the usual way. Okay, so it's some derivative of the joint cumulant generating function. So it's not maybe the most transparent at first definition, but it's certainly the most beautiful definition, just my opinion. J equals 1 up to k of Tj ZL IJ colon alpha j. Okay, so like I said, I'm going to write some examples down in just a second, but I'm just saying that you take the finite dimensional distributions of your process and you study the general mixed cumulants for these finite dimensional distributions. And I'm just giving them some kind of name, and I need to package it into some notation. So I call it kappa with all these extra indices. Okay, but so two examples just to kind of bring this down to earth a little bit. So let's suppose that the index set is just 1, 1, 1, 1. So I'm going to be looking at a single component here, the first component of the vector valued thing Z, and A is alpha, 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 alpha. It's all the same input. Okay, so in this case, kappa L for IA is nothing more than just the usual fourth cumulant of the value of your stochastic process at component 1 at input X alpha. So that's a thing I can study, and certainly I need to characterize this fourth cumulant if my stochastic process is non-Gaussian. This in general is going to be non-zero, and I have to say something sensible about it. Okay, that's one example. Here's another example. So let's compare what happens at two different components of my vector valued thing. So I said in the infinite width limit, they're independent, but at finite width, they're not independent. Okay, so I often refer to n as width, as you already see, because that's how people refer to it in practice. Okay, so here again, I'll take a single input. So in this case, this is a famous thing that physicists write down. So let me write it this way. Okay, so first of all, when you work out the combinatorics, this is exactly the covariance between ZL1 alpha squared and ZL2 alpha squared. Okay, and this is what the physicists call the 4-point vertex, 1 over. So I'm going to write it like this because that's the scale at which it comes in. It turns out to be a 1 over NL minus 1 object. Okay, so this V stands for vertex. So this is the 4-point vertex. The language people often use. Okay, but you can see it's like something that has to do with integrating a polynomial of degree 4 that tries to measure the covariance between two different inputs, blah, 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 or sorry, two different components of your stochastic process at a single input X alpha. And you can just imagine, all of these kappas have a similar interpretation, but I start having to talk about lots of different inputs and I have to talk about lots of different components all at the same time. Okay, very good. So here's the first result. Okay, here's the physics theorem, for which there's partly a mathematical proof, but not exactly in the way I'm going to state it. So in principle, it's a good idea if you have a Gaussian process and you want to do perturbation theory for this Gaussian process to organize things in terms of cumulants. It's a good idea, but no one told you it's a great idea. Like no one told you that the cumulants will, for example, come in at different orders in the perturbation theory and so on. Okay, but it's natural to expect that, and in fact they do. So that's what this theorem says. So it says that as n goes to infinity, okay, you can have an order of magnitude estimate for all of these cumulants. Okay, so first of all, the odd cumulants are 0. Okay, that's just by symmetry, that's trivial. And then the even cumulants look like this. They're a constant which depends on the time parameter, which I will get back to in a second. But for now, L is fixed, and so little l just goes from 1 up to capital L. It's just some family of constants times n to the minus k over 2 plus 1. Okay, and that's when k is even. So this is what the physicists call hierarchical clustering. Hierarchical clustering. That's too fancy of a term, but that's what they call it. But it's the usual thing. If you calculate the cumulants in the law of large numbers, this is the order at which they come in when you approximate the limit. Okay, so just to kind of bring this down to earth for a second, if k is equal to 2, the second cumulant is exactly your 2-point function. And you see that when k equals 2, this is something that survives in the infinite width limit when n goes to infinity. So you get a constant times n to the 0, which is good. That's what's supposed to happen. But then what you see is that the larger k is, the higher the cumulants, the more suppressed it is in the 1 over n expansion. Okay, so let me write this in some now like human computable way, I hope. So thus you can start writing out the full distribution of your Markov chain at time L. So thus, so if I try to write out the density of this thing, so I'll write it P, ZL alpha. So I'll write it like this. It has the following form. So this is going to be a bit of a schematic way of writing it, but I hope it's going to be clear. So I'm just writing the distribution of what the output looks like. So, okay, I can always write the distribution of x minus something. And so, okay, so there's a term that has n to the 0 in it, and then that's quadratic. Okay, this is the thing that, if you were to write it carefully, corresponds to the Gaussian part of your process. Okay, and then there's a term in it which is n to the minus 1 and is quartic in z. So this is like a fourth order interaction. And this is really mediated by, kappa 4. So this v appears here when you properly interpret it. I'm skipping all the constants. And it's like v over n. And then you get n to the minus 2 times zl alpha to the 6th. Okay, and so on. So what I'm saying is, step number 1 is you say, okay, I understand in the perturbation theory at order n what comes in. And the first thing that comes in, the first really non-trivial perturbation, is the fourth order cumulants of your process. So if you just want to know to leading order as n goes to infinity what happens, you only have to study the fourth cumulant, which is great. You get to throw out all the other ones a priori. And so the second part of this theorem is that, okay, we know the order of magnitude of things, but we can actually write down a recursion for all these cumulants. Okay, I'll write down the recursion for the fourth order cumulant, but just like the 2-point function satisfies a recursion, all the cumulants satisfy recursions, and we actually have ways of computing these recursions. Okay, so let me write that like this. So we also have recursions. And this is what I mean by studying things recursively in L and perturbatively in 1 over n. So for example, if you study this 4-point vertex, let me actually do it at layer L plus 1, to make the indexing a little nicer. So it turns out that it equals the following. It equals CW squared over NL times some order 1 constant. Okay, these are again Gaussian integrals from the previous time step. Okay, plus there's some other order 1 constant that you need to compute for, oops, that's not CW, this is K. So this is KL alpha alpha squared times sigma squared of z squared minus 1. That's like a Hermite polynomial times VL alpha 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 over NL minus 1. Okay, so this recursion might look scary, but it's actually not too bad, right? If you assume that you already have solved the 2-point function recursion and that you know the KL at all times, it tells you that the fourth order cumulant at time little l plus 1 is a constant that depends on your nonlinearity at the kernel at the previous layer, the 2-point function, the constant CW, and it comes in at order 1 over n, plus some other order 1 constant that again depends on the kernel at the previous layer, times the 4-point vertex at the previous layer. So this is like now a closed recursion for the fourth cumulant of your process that goes from layer to layer. Okay, and that's the end of what I wanted to say basically about the analysis of this stochastic process at finite values of L. What I'm saying is that we can determine what comes in at every order in the perturbation theory. And we can write down recursions for things consistently at every order. You start with the recursion for the second cumulant that was basically already given to you. You bootstrap that to solve the recursion for the fourth order cumulants. And I've written down kind of the simplest example of that recursion. Then once you have the fourth order cumulants, you can bootstrap the first two to get recursions for the sixth order cumulants. And you know, it really becomes some linear algebra problem essentially to find the answers to these things. Okay, so let me stop. I know I'm sort of saying a lot of stuff, but I hope it's like human computable. But if it isn't, you should tell me, and I'll try to answer questions for a minute or two if there are any. And if not, I will tell you about sort of what happens when you do the large L analysis and why it's related to kind of like criticality in certain like stat mech systems. At least that's how we think about it, and what some of the results are, and okay, so on and so forth.
Boris?
Yeah.
Are you gonna say something about finite L but different alphas?
Sorry, so yeah, so all of our results work for any alphas you want, but it's just when the alphas are different, when you have multi-point functions, the recursions look a little uglier. Like, for example, you know, here there are 4 alphas, right, that go into the fourth cumulant, and you see that there's a sigma to the fourth here. And it's all evaluated like at alpha. So if I had different alphas, then I would have to write, like if I had alpha 1, alpha 2, alpha 3, alpha 4, then it would be sigma alpha 1, sigma alpha 2, sigma alpha 3, sigma alpha 4 in here. So the tensorial structure in the alphas is pretty easy. And like, you know, this sigma squared would be like sigma alpha 1, alpha 2, sigma alpha 3, alpha 4.
Got it. Thanks.
And similarly here, and, you know, similarly here, like everything is kind of has the right order. But yeah, it's just a little easier to write down the single input thing. But yeah, of course the recursions are for any number of inputs. It'd be pretty sad if we only had the 1 point kind of corrections. Yeah. Other questions? Yeah, I just tried to write it schematically. I should have emphasized that. You know, when I say this, I really mean we have the formula when this is the joint distribution over all the components of this process and all the alphas, you know, all at the same time. We have nice recursions. And then you can go through and you can write down these recursions, and then you can solve them for the cases that are kind of interest. Like the single input case is particularly easy to solve. I just wrote down the recursion, you iterate it, you just got the solution. It's slightly more painful when you have more alphas, but you know, it's doable. Okay, last chance, no, I'm kidding. Okay, so if there are more questions, you should again just stop me in the middle. You can also put them in the chat, which I can see. Okay, so let me now tell you what happens at large L. This is quite interesting, and then I hope I will have a couple minutes at the end to explain how to see all of this stuff in the random matrix product world. There's a very simple example you can compute, but let me not get there yet. So this is large L behavior. Okay, it's quite natural to now say I have 2 perturbative parameters. I have, you know, L can be large and N can be large, and I'd like to study what happens when potentially both of them are large. And the first question you have to ask is, you know, when does your Markov chain have any kind of well-defined limit at all? No one told you it has an interesting limit as L goes to infinity. Like it could be plus infinity almost surely, or 0 almost surely. And then, you know, there's, okay, that's an easy thing to study, but obviously it's not interesting. Right, so the question is, for which values of the model parameters, you know, the things that define the system, does the Markov chain ZL have a good behavior at large L? And the way that at least my collaborators think about it is, you think of the sigma as basically being given to you, you know, someone tells you, but then CB and CW are 2 continuously tunable parameters that determine the dynamics of your system. And if you want really good behavior, what I'm about to say is you have to tune them very, very carefully. There are certain specific values you have to set them to. And at those values, you get some nice kind of behavior. And at those values, your system is basically at criticality. Okay, that's the kind of thing that I'm about to try to say. Okay, so before I give you the general thing. Let's just do an example, just so we can kind of get a sense of what's going on. So let's do the simplest example, sigma of t equals t. Okay, CB equals, actually, I don't want to set CB to 0 yet. All right, so let's just consider only the Gaussian process part of just matrix products. That's something that's obviously very analyzable. So let's look at the recursions that we had, and I'll remind you, right? So here the recursion for the 2-point function was k l plus 1. I'll write actually the, let me write the 1-point thing first. Actually, let me write it this way. So what is this thing? Right, you can think of it like this. This is just the expectation of 1 over n times 1 over nl sum nl plus 1, the way I wrote it. J goes from 1 up to nl plus 1 of z l j alpha squared. Okay, so of course the j's are all symmetric, so it's just the 2-point function of your process. But I want to think of it this way. This is like, you know, my original process was vector valued, and this is just the average size of the like vector that I have at time l plus 1. Oops, this should have been an l plus 1 as a result. Okay, so the recursion that we had for this thing said that this was CB plus CW times, well, what do you have? You have sigma squared of Z, you know, with respect to the previous layer kernel. So here Z was just a Gaussian random variable with mean 0 and this variance. And in this case, sigma is just the identity. Okay, so you get a very simple recursion in this case for the 2-point function of your process. You just get this. Okay, so you know, to determine whether or not you have good behavior at large L, you basically have to solve your recursions and you have to see what happens. That's what I'm trying to do. And I'm just trying to do it in the simplest case to give you a sense of what might happen. Okay, so when you study a sequence of Gaussian processes, you know, to ask about regularity of that sequence, you basically are going to ask for regularity of the covariance functions. So that's what I'm doing. So regularity number 1 is I'm going to say, well, I kind of want the on diagonal behavior of the covariance function to remain reasonable. I want it to like remain bounded. Okay, and then regularity number 2 is I want the derivatives of my stochastic process to be bounded on average. So this is about the jets of the 2-point function on the diagonal. Okay, so I'm going to write it this way. You take the derivative with respect to x alpha, x beta, and then you set x alpha equal to x beta. Okay, and when you work this out, this is nothing more than the expectation of 1 over nl plus 1, sum on j goes from 1 up to nl plus 1 of the norm of the gradient of your process, l plus 1, j alpha squared. Okay, so this is like another thing I could study about my process. I want to say not only is the variance the same or like staying reasonable at various points, but I also want the derivative to be reasonable. I don't want it to be highly oscillatory. Okay, and when you go through and you just apply this operator to the recursion for the 2-point function, what you end up finding in this case is just that this is CW times the relevant derivatives of the thing at the previous layer. An easy calculation, but I skip it. Right, you just differentiate this recursion and then you compute the resulting Gaussian integral, and it's not too bad. So what I'm saying is that you have nice L goes to infinity behavior, at least in this case, only if what? Well, okay, look, the recursion for the derivatives is just that you multiply every time by CW. So unless CW equals 1, you're totally screwed. You know, if CW is bigger than 1, your gradients on average are exponentially growing with L. If a CW is less than 1, they're exponentially decaying with L. Okay, so I have to set CW equals 1. But then if CW is equal to 1, I now look at the variance of my process. And okay, CW is now equal to 1, and I have to have CB equals 0. Otherwise, the variance is going to keep growing with L as well, and I'm going to have some bizarre process that I can't study. Okay, so CW equals 1, CB equals 0. And this is like the simplest example of needing to tune CB and CW carefully in order to have some well-defined or as nicely defined limit as you can when L is large. Okay, so for general sigma, we have a procedure for doing this. Okay, so we ask that this equation V and this equation G for values and gradients. So if we ask that maybe I'll just actually write it this way, KL plus 1 alpha alpha is equal to KL alpha alpha. And we ask that these mixed derivatives of the covariance kernel are invariant as I go from one layer to another, KL alpha beta, then the resulting values of CB and CW are, okay, so we introduce some words for this, are tuned to criticality. At least that's the term we typically use. Okay, so I'm just saying to study the large L behavior, you need to set the model parameter somehow. And we have some prescription for how to do this for any sigma you want. You give me the sigma, I plug through these kind of equations, and there's some way of setting CB and CW so that you can do things. Okay, and if you like this kind of physicsy point of view, like, you know, there's some trivial theory in like the large N limit, right? Here, literally N is the width of the network, and it's like the large number of particle limit if you want. And it's like a non-interacting free Gaussian theory. And what we're asking for is to tune the parameters of the Hamiltonian so that that theory is invariant at different scales. You think of the time parameter L as changing the scale of your theory. And now what we're going to do is we're going to study basically like the flow for something like the renormalization group. Okay, big words, but I'm just saying when we change L, but we have the finite size effects to worry about. When N is finite, we're interested in what happens to the theory. That's kind of the questions that we're studying, at least in that language. Okay, so I've defined what it means to be critical, that there are certain settings of CB and CW so that at least the Gaussian processes are well behaved in the infinite width limit. And now I want to study what the corrections to the Gaussian processes actually do. Okay, so hopefully that was more or less clear. Now I'm going to be at criticality. So if you're not at criticality, there's nothing interesting that happens in the sense that everything is either exploding or blowing or vanishing exponentially with L. And the theorem goes like this, that at criticality, you have that these higher order cumulants of your process. Okay, so here I'll study directly the even cumulants, so 2K point cumulant, which I wrote like this before. So they actually look like this. They're a constant that depends on sigma. So before they looked like n to the k minus 1. That was the order at which the kth, so the 2k connected point function, i.e. the 2k cumulant of your process used to be suppressed like 1 over n to the k minus 1. And it seemed like it wasn't going to be important. You know, like there's no reason to study anything past the 4th order cumulant. But actually life is hard. Okay, and the point is here you get L to the k minus 1. That's what the dependence on the depth actually looked like. Okay, so in fact, there's a new parameter which appears, which is L over n. And you can now try to imagine taking the limit of your stochastic processes when L over n is fixed and both of them are going to infinity. And you're going to get a very interesting non-Gaussian stochastic process, right? And it's non-Gaussian because all the higher cumulants survive. It's not just Gaussian plus 4th order cumulant, for example. It's like all the higher cumulants are there, and it's an interesting question what this process is, and so on. Okay, so let me write it this way. So that is, okay, we have, so I'm saying we solve the recursions, and we can determine the behavior in large L of these recursions. So if I wanted to write down the distribution of the outputs now, it looks a little bit different. So it's x of minus, okay, so now you still have a Gaussian part, z L alpha squared, okay, and this Gaussian part is well behaved precisely because I'm at criticality. I basically ask that the Gaussian part is well behaved. That's like asking that the 2-point function has a nice kind of behavior in capital L. But now there are interesting corrections. There's an L over n correction that's quartic in z. And there's an L over n squared correction, you know, which is 6th order in z. Not sure how to actually say that in the Latinization of it and so on. Okay, so now your Markov chain does something kind of wild and interesting, and it has a non-trivial double scaling limit where you send both n and L to infinity, and it's no longer Gaussian. And okay, this has all kinds of consequences for neural networks. That's why we were originally excited about it, but it just strikes me as a kind of beautiful class of processes to study. And let me try to like drive that point home by doing, this is great, I have like 5 minutes, or maybe 7 minutes. And I'm gonna do one example for you to try to show you this appearance of L over N in some way that maybe will be organic. Okay, so before I do that, I got too excited and I forgot to ask if there are any questions or people have comments. So let me do that now, and then I will do the random matrix product example.
So
what
in
is-
the heuristics you showed so far, you first take n to infinity and only then L to infinity, but now you're going to show us like a heuristic for taking them both to infinity at the same time.
Yeah, correct. So that's a really good point, and I should have said that more clearly. So the way we approach the problem is we said, okay, we don't know what happens at large L, but we know what happens at large N. So we're going to first fix L and do the perturbation theory in N. And you're going to have some power series in N for everything imaginable. Then we're going to try to solve those recursions in L. You know, and a priori, there's no reason to think that 1 over n terms and 1 over n squared terms will ever talk to each other. But it just so happens that when you solve those recursions, the 1 over n term is only multiplied by L, but the 1 over n squared term is multiplied by L squared. And so now they do talk to each other. And yeah, I'm about to give you a kind of way to think about why they talk to each other this way.
So Boris, you write the physics theorem and not the theorem because you cannot justify the change of order of limits?
No, so the kind of things that we do are actually, they're not too bad. You know, everything could be mathematized, I'm sure. But we basically just assume that there are 1 over n expansions for things. And then we write down recursions for the terms. But, you know, formally speaking, you have to like identify that there's a leading order term plus little o of 1, subtract off the leading order term, show that the, you know, result times n is leading order, or like is o of 1. And, you know, so you have to kind of justify the recursions way more carefully than we do. So there's some things, but there are no path integrals. There's no replica symmetry breaking tricks. You know, there's no things which there'd be no hope to do. It's like, I think it's possible, but it's not that easy. There's like, at least it doesn't seem easy to me. Maybe it's easy to somebody here, and then I would be very happy to hear about that. Yeah. So I'm just trying to be careful. You know, some of the things I know how to prove exactly, but certainly this thing I don't know how to do. So I don't want to claim that like I have a manuscript in which I could give you a proof that a mathematician would like. But for on the physics level, you know, it is okay. At least that's what my collaborators claim to me. I can't tell. Yeah. Other questions while I draw my middle line here? That's not a very good one. It's better.
Size of your input data is fixed and 0.
Yeah, so if you want, here we're studying like the finite dimensional distributions of this process. So you think of the, you know, the number of points in your finite dimensional distribution is like the size of the input data, roughly speaking. So we think of that as fixed and the other parameters as being relatively large.
And did you study what happened when this is going to infinity or that's...
Yeah, so that's a really good question. There are quite a number of subtle things that happen when the size of the input data goes to infinity. Like if you just think of Marchenko-Pasteur distribution, you know, like the ratio of the 2 parameters is actually quite important. But let me put it this way. For the Gaussian process convergence, that very first theorem I stated, I do know how to prove the theorem that you get tightness as well. So you really get convergence of the full process, not only of the finite dimensional distributions. So at least in that sense, I can get away from just the finite dimensional marginals. But still, you know, that version of convergence is not good enough to deal with what happens when you have like a very large number of points at which you evaluate things. And it's subtle and interesting, and I don't know. That's the truth. You know, I could bullshit you, but and I still might later, you know, but for now, let me be honest.
Right, thank you.
Yeah. Okay, so am I allowed to have another 3 minutes? Is that how this works? Okay, excellent. So let me do an example. Okay, maybe arguably I should have started with the example, but I wanted to get through the new stuff. So let me go back to this random matrix product example. Right, so here ZL alpha is just WL down to W1 X alpha. Okay, so let me show you that there's an interesting joint scaling limit, even in the random matrix product case, where N and L are large. Okay, so all my NLs are here equal to N. So, so let's do it. First of all, okay, this is very trivial, but remember all my matrices are Gaussian. So the direction of this vector is just uniform on the unit sphere. So that's easy. And it's independent, in fact, of the norm. So all we have to do is now study the norm of this thing. Well, okay, the norm of this thing you can do exactly. No one can stop you. So we can do it together. Okay, let's do it. So I'm going to use the fact that my matrices are Gaussian here. It's actually not very important. All this should be universal as long as you match a couple of moments. But I don't know how to do it otherwise, you know, at least in the physicsy stuff. We really use Gaussianity in various places. Okay, so I'm going to study the size of this thing by doing the most naive thing I can. So I'm just going to multiply and divide by the norm of the first term. Okay, that's a true thing. Okay, and now the observation is just that these two things are independent. Right, this is just a uniformly distributed vector on the sphere, and this is the norm. So what you get is that when you iterate this equality, you get an exact equality in distribution. So this is the product on L goes from 1 up to capital L of the norm of WL times, let's say, a fixed unit vector U. Okay, if you're being very careful, you also have to have the norm of X alpha out in front, just to make this first thing a unit vector. Okay, so that's nice. That's very good. And now let's remember that, you know, the WLIJ were Gaussian with mean 0 and variance CW over N. Had this parameter CW in there. Okay, so when you write that out, what do you get? You get CW to the L over 2 times the product on L goes from 1 up to capital L, and you just get a chi-squared random variable with n degrees of freedom that's, you know, normalized by 1 over n times the size of X alpha. Okay, so this prefactor here is the thing that's responsible for criticality. If you don't set CW equal to 1, you are going to have a poorly defined large L limit anyway. So now I set that equal to 1. And what do? I write this like this. I write this as the exponential of the sum on L goes from 1 up to L of the logs of these random variables. Okay, maybe with a 1/2 times the size of the initial input. And, you know, the whole point is that these guys are IID. You know, these are IID draws from this distribution. So I can just apply the central limit theorem. Okay, and when I apply the central limit theorem appropriately, I get a Gaussian mean minus L over 4n and variance L over 4n. And you really see the L over n appearing. So there's an interesting resummation that happens, and you see that because it's e to the Gaussian, all the orders in L over n are kind of important there. And so rather than getting a Gaussian limit, you get a log normal limit. So it's really different when you take the joint scaling limit in L and n. And it's really fascinating to ask what happens to the spectrum of this matrix product in this limit. There's some interesting papers about that now, and I'm excited about that too, and so on and so forth. But I'm saying, like, there's a relatively straightforward thing you can write down, at least just like for these very simple-minded statistics, just, you know, the norm of what happens when I apply a matrix product to a fixed vector. And it already depends on L over n. And then, of course, all the further questions, when you add the nonlinearity in there, when you ask about the spectrum rather than just the kind of linear statistics and so on, have an L over n kind of behavior as well. And it's certainly not fully understood. Okay, so let me stop. I promised to take 3 minutes and it took 4 minutes, but hopefully that's okay.
Okay, so let's thank Boris. Any questions? Or we'll let Boris go back to sleep?
Yeah, I have a question. If we're already looking at this from a physics point of view, I wonder, I mean, many things here look a lot like the, you know, there's the state evolution equations for belief propagation. This, like, all of these, like, kind of look like those, you know, message passing iterations, and then you have the state evolution equations, which are kind of like a central limit theorem. I wonder if there's any way to fit this into that theory. Have you ever thought about it, or do you know anything about it?
Yeah, so the short answer is, okay, I'm not 100% sure, but I think what's probably true is that they look the same, not because one really fits into the other, but because both of them are just like some method of stationary phase. You know, like you have some saddle point approximation to some infinite n system, and you're computing the one loop correction, the two loop correction, and so on. You know, like somehow message passing is easy on trees, and then you have to have loops. And of course, a similar thing is happening here, right? You have some like free theory in the infinite n limit, and then these like cumulants in the physics language are like some kind of like loop corrections to that theory. And we're like actually writing down the diagrams basically. And then like the fact that sigma is nonlinear makes the diagram counting harder, but okay, you do something sensible and it sort of works out. But I'm not sure, you know, there could be that some part of that literature, which I really don't know well, maps on exactly to this kind of thing. But it's a little hard for me to tell from my point of view.
Thanks.
Yeah.
Any further questions? Okay, so thank you, Boris, for 2 hours of fun. And thank you, everybody, for joining. And see you next week. Bye-bye.